7 for the work that he did in the Krebs cycle. And this is a cycle involved in cellular respiration that we'll be talking about today. One of the sayings that I like to pick up from him is that think boldly, don't be afraid of making mistakes. So especially this applies to your homework, right? Don't be afraid of making mistakes in your homework. It's okay. Don't miss the small details, but keep your eyes open and look at the larger concepts and be modest in everything, except for your aims, your ambitions. So, as I said, he identified many of the steps in the cycle that we will be talking about today, which is variously called the Krebs cycle, or the TCA cycle, the citric acid cycle. He isolated vitamin C. So vitamins are also very important to this process, as we'll see. And if that wasn't enough, this gentleman also pioneered the chemistry of muscle contraction, which we won't be talking about this term for the next term for sure. So the last lecture and this lecture and your next lecture will be all about how energy is used. So obviously light energy comes into the earth from outside, and this is converted into structures, which is basically a way to hold energy through photosynthesis, so it makes organic molecules. And then what respiration does is to take the energy out of these organic molecules for other kinds of work, and specifically the energetic molecule that acts, these little packets of energy for work in other processes is ATP. There's some other molecules involved as well, but ATP is the main one. And then through respiration, these organic molecules are broken down into carbon dioxide and water. And of course, these are the starting components for photosynthesis. So it's a wonderful cycle of things. So today's lecture is going to be about respiration. This is what happens with Macs sometimes when you're using Keynote. At least my Mac. So this is the overall picture for respiration. You have these organic compounds, add oxygen, and you get carbon dioxide, water, and energy. So this could be many different kinds of organic compounds, but today we're going to be focusing on glucose, just as an example of respiration. So glucose, C6H12O6, combines with 6 molecules of oxygen to make 6 molecules of carbon dioxide, 6 molecules of water, and energy. So the free energy that is potentially released under standard conditions is negative 686 kilocalories per mole. And does this mean that energy has to be put into the system or is energy released by the system? Released. And so what do we call that? Exergonic. So this is an exergonic reaction. It should occur spontaneously, but as you may know, you can keep like glucose in the jar and there's plenty of oxygen around and the glucose just sits there without doing anything. So explain that. There's an activation energy that's required. So these have to go through some kind of intermediates before they're actually broken down into carbon dioxide and water. And that activation energy is overcome in cellular respiration, probably through what? Enzymes. Right? So enzymes reduce that activation energy, as you remember from Dr. Cussel's lecture last time. So during respiration, there's another kind of chemical reaction that occurs, and you can think of this as an oxidation reduction reaction. They are, in fact, oxidation reduction reactions. So what is a reduction reaction? It just means that there is a gain of electrons. And it's called reduction because when you add a negative, right, then you're reducing the sum of the charges in this case. oxidation necessarily requires oxygen per se, but it's just the opposite of reduction. Okay, so that would be the loss of electrons. So in this example, what is being reduced and what is being oxidized? Here we have sodium, and the valence in the shell for most outer shell of sodium is what?
Sodium is getting oxidized.
It's getting oxidized, and that's because what?
It's lost an electron.
So that electron, that one electron in the outer valence shell tends to be lost. Okay. Or, what about chlorine? What's the valence for chlorine? The valence is 1, 2, 7, 14, 7. Yeah, that's right. So it tends to pull in electrons to complete its valence shell of 8, right? So if it's pulling in electrons, what's happening to chlorine? It's being reduced, as you can see here, by these little plus and minus symbols. So the charge here is being reduced because it's an electron acceptor, and here this is becoming positive because it has lost an electron. Oh, there's the answer to it. So more precisely, chlorine actually exists in a gas as this molecule. And so 2 electrons are actually being added to the shells, the valence shells of chlorine, to make them ions. And then there are 2 molecules of this metal, sodium, type 1 metal. And so it's actually releasing its electrons, becoming also an ion. So that's the sum of those reactions. And we can also think of oxidation and reduction reactions as not complete, like the kind of reaction that we just saw, but where there is a change in the energy state of electrons. So remember, electrons really are all about bonds, or bonds are all about electrons. And so when there are rearrangements of bonds, then the energy states of these electrons are actually changing. And so the oxidation reduction states of different parts of the molecule are changing as well. So here's another reaction to consider. This is the combustion of methane gas. So here's methane. It's CH4. This is what the structure of it looks like if you were like smashed against a flat plane. And then these little dots here represent the valences or the electrons in the outer shells, right? So you can see that the electrons here are kind of halfway distributed along the bonds. And that's pretty close, pretty accurate if you think about the actual structure. So they're being shared almost equally between hydrogen and carbon. When methane becomes oxidized by combustion with oxygen, there's a change in the distribution of those electrons. And so oxygen is what? Electrochemical. What is it? It's electronegative, which means what? It tends to soak up electrons, right? It tends to attract electrons. And that's exactly what's happening here. You can see the electrons are being attracted more over to the oxygen side.